Hello everyone. Let's spend some time reviewing a bit about drawing cyclohexane and thinking about the chair-chair interconversion. You'll see I don't have my molecular models with me. I'm going to do it on the board, but you should work through this video with your molecular models close at hand so that you can see the correspondence between what we're drawing and what the model of chair cyclohexane actually looks like. So the first thing you should do is you should pause the video and you should draw your best cyclohexane in the chair arrangement. So feel free to put your cyclohexane model in the chair arrangement. Remember that you'll often see cyclohexane represented in this way. There are 12 hydrogens going around the ring. I won't fill them in. But we know that cyclohexane's energy minimum arrangement is not a flat planar one. It's a so-called chair. So can you draw that? Again, to review some of the tips, the drawing tips that we went over in class, one of the keys in drawing the cyclohexane chair is to keep the bonds that are opposite to each other in the chair structure parallel. So if you start with two parallel lines that are a little bit offset like these are, and then you go from there and you draw two new parallel lines like that, and then finally there are two more bonds that we haven't shown here. I don't know, some of these colors don't show up very well on this particular blackboard, but this line then should be more or less parallel to that line. Okay? So there is the cyclohexane chair type of drawing. Again, opposite sides are parallel. It's key to a good drawing that you have this kind of offset of the lines, and then you have parallel, 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 parallel. And it shouldn't look like a bow tie. It should really look more like the model would. Okay, so you want to look at this from the right perspective. Okay, so hopefully you were able to draw the cyclohexane chair, and this is something you just need to practice and practice and practice. So wherever you are, if you're out for coffee and you're sitting there in the coffee shop or wherever, and you've got your piece of paper or you've got your napkin and you've got a pen or a pencil, just draw cyclohexanes in the chair arrangement wherever you go. Okay, so the next part of this is to fill in the hydrogens. There are 12 of them, so we'll have to fill in 12. And let's start with the ones that I claim really are easier. Let's start with the axial ones, okay? And remember, they alternate axial down, axial up, axial down, axial up as you go around the six-membered ring. So again, pause the video, fill in the axial hydrogens. Start at a corner. Here we go. Does this corner point in the general direction up, or does it point in the general direction down? Well, it's pointing up. So the axial hydrogen, let's see, I'll put my axial hydrogens just in white chalk. That axial hydrogen will go up. So once you do that, then you just go around the ring alternating axial up, axial down, axial up, and then use this little artistic device here, leave a little gap in the bond that's in the back just to keep track of what's behind and what's in front. Axial down, axial up at this carbon, and then axial down, this bond goes behind this pink bond that's in the front. So hopefully that's 1, 2, 3, 4, 5, 6 axial hydrogens. Have you built a model of this? If you take your model that you think is in the chair arrangement, remember if you just take that model and you put it down on a flat surface like the table, it should just very nicely sit on this tripod of 3 axial down hydrogens. If it doesn't seem to be sitting like that, you probably have some problem with the shape of the ring. It's not really in a chair. So those are the axial ones. There's 6 of them. The other 6 are kind of around the equator of the ring. So remember, they're called the equatorial hydrogens. So can you fill in the 6 equatorial hydrogens, and let me just remind you of a couple guiding principles. So first of all, at each carbon, there's a group that's in the up direction, and there's a group that's in the down direction. Now, the down direction may not be as dramatic as this, axial down. It may be equatorial down like that, but at every carbon, you should check that if you have an up group, you also have a down group, okay? And then the other concept is that the equatorial bond, so I'll fill this one in for you, right? So there's an up hydrogen here. There should be an equatorial down hydrogen there. And so this bond right here, maybe I'll use a different color. How about I put the equatorial hydrogens in yellow. This equatorial bond is parallel to these 2 pink bonds. So I referred to those bonds as the carbon-carbon bonds of the ring once removed from where this is. So check that this is parallel to that, this is parallel to that. Okay? And do that as you go around the ring. Okay, so you pause the video and fill in the other 5 equatorial hydrogens in this molecule. Okay, let's work our way around here. So this carbon already has an axial down group. So the equatorial substituent will be up like that. So, sorry, this is supposed to be yellow like that. So you see how this bond is parallel to this bond and that bond. Here's one that sometimes gives people difficulty. Here's axial up. I need an equatorial down bond, and I need it to be parallel to this and to that, so it goes right there. And then axial down, equatorial up. This should be parallel to that. This should be parallel to that. This one, axial up, so I need an equatorial down bond there. And this one should be parallel to the orange bonds there and there. And finally, this one is probably the hardest one for people to do. So if you haven't filled that in again, give it a try. Well, this already has an axial down hydrogen, so it should be equatorial up. And it should be parallel to the bond once removed, that one or that one. So your drawing should have the 6th equatorial hydrogen there. Okay? So just to recap, draw the backbone of the cyclohexane ring. Be sure that the opposite bonds are parallel when you do that. Once you're satisfied with that, I recommend filling in the axial hydrogens, alternating axial up, axial down, axial up, etc. around the ring. And then the last thing you would do would be to fill in the equatorial substituents, being sure that each carbon has an up group and a down group, and being sure that the equatorial bonds are parallel to the ring carbon-carbon bond that's once removed. Okay? So do that 10 times, and I think you'll be well on your way to being a good cyclohexane chair drawer. Let's do another cyclohexane drawing problem. But let's make a derivative of cyclohexane this time. So here's just my cyclohexane ring. And so now what I want to do is I'm just going to substitute it. I'm going to replace one of the 12 hydrogens with a methyl group. So this would be methyl cyclohexane. And what I would like you to do is first start by drawing the cyclohexane chair, your best cyclohexane chair, and then replace one of the 12 hydrogens with a methyl group. And let's see how that goes. And let's start by replacing one of the equatorial hydrogens with the methyl group. Okay, so we're going to start. We're going to draw the cyclohexane chair. I showed you in a previous video segment how to do this kind of systematically. Let me show you how I actually tend to do it. You get the same result, but if you want to see, kind of how one could do this in a slightly different way. So I start like that with like a little, looks like a bird's beak or something like that. And then I build the rest of the structure off of there. So this bond is parallel to that bond. And then I'll finish it off with another piece like that. All right? So if you draw your cyclohexane chair in some other way, that's perfectly fine. But just to show you one possible way to do this. Okay, so now I need to put the methyl group in an equatorial position. So let me just go ahead and put in all the axial hydrogens. So axial up, axial down, axial up. You can put a little gap in the bond in the back there, etc., etc. And there. And then let me just put my equatorial methyl here. For the purposes of this problem, it doesn't really matter where you put it. You should convince yourself, maybe with your molecular models, that wherever you put the equatorial methyl, you can turn the model to make your model look exactly like this drawing. Okay? And let's see, I've got some equatorial hydrogens to fill in. So here's one. Notice that bond is parallel to this bond and this bond. I'll put the other equatorial hydrogens in as well. Okay, so hopefully you came up with something at least equivalent to this. If you drew this in a slightly different way, or in what looks to you to be a different way, make a model that reflects exactly what you drew, and then see if you can turn that model over or upside down or whatever, and try to convince yourself that it's actually equivalent to what I've drawn here. Okay, so this methyl group is in the equatorial position. And now what I would like you to do is to carry out this process that we called chair-chair interconversion. Or CCI, if you prefer an abbreviation. And remember, that doesn't just entail taking the whole model and turning it upside down or rotating it or anything. It's actually a conformational change of the molecule. And as we said in class, a good way to think about this is to take your model and take this carbon and move it up like that, and take this carbon and move it down. So as the name suggests, you're going to start with a chair arrangement, and you're going to end up with a chair arrangement. So see if you can draw the other chair form of methyl cyclohexane via this kind of chair-chair interconversion process. So pause the video and give that a try. Well, over here, let's keep track of this carbon. So let's call this carbon 1, and then let's just go around the ring 3, 4, 5, and 6. So I'm going to move carbon 1 up. When I do that, so I showed you kind of how to draw cyclohexane using this kind of beak-like strategy. So carbon 1 now, instead of being down here, is going to be up here. Here it is. And then I need to build the rest of my ring off of that, like that. So carbon 1 moved up like so. Carbon 4 moved down. So hopefully carbon 4 is pointing down now. Yes, it is. Okay, so that's comforting. There we go. 1, 2, 3, 4, 5, 6. And then the issue has to do with keeping track of the groups, right? So it seems like carbon 1 is pretty important as far as we're concerned. As this carbon moves up and ends up where I drew it on the right-hand side, I think you can see that this methyl group, which starts out equatorial up, so this is equatorial, and it's in the up position, whereas this hydrogen is down, right? It's going to end up here. And the hydrogen on one is going to be there. So notice what happens, right? So remember what we said about chair-chair interconversion. When you chair-chair interconvert, all the things that were originally equatorial, like this methyl group, become axial. And all the things that were axial, like this hydrogen, become equatorial. So this hydrogen is now equatorial. This hydrogen here was axial. And then how about the upness or downness of a group upon chair-chair interconversion? So focus on the methyl. It started out equatorial up, and it ended up what? Axial and still up. And the hydrogen, which was axial and down, has now become equatorial and down. Okay? So can you make a little synopsis of what happens to axial groups and what happens to equatorial groups upon chair-chair interconversion, and what happens to up groups and what happens to down groups when you chair-chair interconvert? Just a little table maybe. So here's the chair-chair interconversion process, right? We know now that axial groups chair-chair interconvert and give equatorial groups. Up groups upon chair-chair interconversion remain up. And down groups, when you chair-chair interconvert, remain down. So the upness and downness of a group is preserved upon chair-chair interconversion, but the axial and equatorial nature is interchanged. Okay? All right, so hopefully you're able to think about that. The next question is, which of these two conformations, so this is the methyl equatorial, and this is the methyl axial, which of these two conformations is more energetically favorable? So this is a concept that you should kind of know just right off the bat. Is it generally speaking, I mean there's always exceptions, but generally speaking, in the vast majority of the cases, is it more favorable to have a given group in an equatorial position or in an axial position? It is more favorable to have the group in an equatorial position. Okay, so this side is thermodynamically favored. Okay? So in class we didn't quite get a chance to explore that, maybe as much as we would have liked to. So it's conformational analysis like we did when we did the conformational analysis of ethane or propane or butane or what have you, where we look for the types of interactions that we're familiar with, eclipsing interactions, gauche interactions, those sorts of things. And we try to compare the two sides of the equilibrium, the equatorial methyl versus the axial methyl. Okay? So first question, are eclipsing interactions going to be an issue on either side? Why or why not? Well, eclipsing interactions are not going to be an issue because remember, chair cyclohexane is completely staggered all around the ring. So take your model, look down any of the 6 carbon-carbon bonds of cyclohexane, and what you will see is a perfectly staggered arrangement. That is to say, there's no torsional strain associated with cyclohexane itself. Okay? Everything is perfectly staggered. What about other types of interactions, though? So what I would like you to look for is in each of these arrangements, look for gauche interactions. All right? And it's going to have to do with the methyl group. So what I want you to focus on are the bonds that connect carbon 1 to the adjacent carbons. All right? So this bond right here, the bond between C1 and C2, and this one, the bond between C1 and C6. Take your model. Maybe you have enough pieces to make two different models. Put one model so that the methyl group is equatorial. Build a second model of methyl cyclohexane, but arrange it so that the methyl group is axial. And what I would like you to do is I would like you to look down this bond, and then look down this bond. And then on this model, look down that bond between 1 and 2. Look down the bond between 1 and 6. And look for interactions involving this methyl group. All right? So do that. Maybe do this along with a friend and discuss what you see. And then come back to the video. Okay, so we're going to be looking down this bond. And what I want you to focus on, as you look down the bond between 1 and 2, I want you to focus on the dihedral angle between this bond between C1 and the methyl, and this bond between C2 and C3. Okay, so if I put my eye right along the C1, C2 bond, go ahead and do that. What's the dihedral angle? And you might be able to answer the question just by looking at this picture. But what's the dihedral angle between these two green bonds? Well, the dihedral angle is 180 degrees. What do you call two groups that are 180 degrees to each other? Those two bonds are anti to each other. Okay? And then look down the bond between carbon 1 and carbon 6. I've got to put my eye down here somewhere. And what's the dihedral angle between this carbon-methyl bond and this carbon-carbon bond that sprouts off of C6? What's the dihedral angle there? Well, that's also 180. So those bonds, my drawing's getting a little crowded here, I apologize for that. So those bonds are also anti to each other. Okay, so you might want to pause the video again and go through that same exercise in this case. Look down the bond between 1 and 2 or between 2 and 1. Look down the bond between 1 and 6 or 6 and 1. And think about the relationship of this carbon-carbon bond to the methyl group and those same two bonds, the 2,3 bond and the 6,5 bond. Well, here's the 2,3 bond right here. And here's the 5,6 bond right there. So if I'm looking down the 2,1 bond, go ahead and do that with your model. It's much easier to see it with the model. You've got to put your eye right along that bond. What's the dihedral angle between this orange bond and that orange bond? They are 60-degree dihedral angle. And what's another name for a 60-degree dihedral angle? Those bonds are gauche to each other. And then if you put your eye along the 1,6 bond or in the 6,1 direction, you can look in either direction. What's the relationship between this carbon-carbon bond and this carbon-carbon bond? Well, those are also gauche. Okay? So does that help in terms of conformational analysis? Think back to N-butane. What was the lowest of the low conformational energies for N-butane? What conformation? It was the anti, okay, where the two methyl groups were as far apart from each other as possible. And then the gauche was a little bit higher than the anti. Do you remember by how much? By about 0.6 kcals per mole. The difference in energy between these two arrangements, the methyl being equatorial and the methyl being axial, well, what would you estimate it as? Count the number of gauche interactions in the orange case and compare it to the number of gauche interactions in the green case, and then do the math. Well, how many gauche interactions are there here? None? 0? How many gauche interactions are there here? 2. If each gauche interaction is worth about 0.6 kcals per mole, we would predict that this would be at about plus 1.2 kcals per mole relative to this one, which would be our base mark. So we could just declare this to be 0 kcals per mole. Remember, we don't care about an absolute energy scale. It's all relative. Okay? So this one is lower in energy than that one. Which side is going to be favored at equilibrium, given that the green side is lower in energy than the orange side? Well, this should be favored at equilibrium. The answer is actually right here. Thermodynamically more favored. So, you know, we could modify the length of our arrows or something to reflect that. The actual difference is a little bit greater than 1.2 kcals per mole. The actual methyl A value, an A value is just what is the energy penalty for putting a group axial versus equatorial, and it's going to vary in magnitude depending on the group, but the axial value for a methyl group is about 1.7 kcals per mole. But our estimate was not too far off. Okay? So what you should definitely remember is it is better to have, energetically speaking, better, lower energy, to have a group R in an equatorial position, in this case the R group was a methyl, versus an axial position. And that effect comes from this phenomenon where you have more types of energy costing interactions when you have a group axial than when you place that group equatorial. Let's look at the following. Carbocation fates. In other words, what are the things that happen to carbocations? And let's just take one step back and let's imagine that I just put an energy axis like this. And I realize that all of our energies are always comparative. We're comparing one thing to another. But if you generally think of high energy stuff being up here and low energy stuff being down here, can you put a carbocation on this diagram? Just whatever carbocation you want. You don't even have to specify its exact structure. Just put it somewhere on this diagram. And also specify whether it's a local energy minimum or a local energy maximum. In other words, is it one of these or is it one of those? A carbocation is one of these. It's a local energy minimum, but it's a high local energy minimum. So, you know, we might put it up here somewhere. So right there there's my carbocation. The point is twofold. First of all, I want you to know that a carbocation is a local energy minimum, not a local energy maximum. It's not a transition state, it's an intermediate. Second of all, we might expect carbocations to not hang around very long. They're going to be quite reactive because, well, you're way up here, and if you can just overcome some small barrier maybe, you can go on to product. Okay? So I want to start thinking about our list of carbocation fates. We will have a grand total of 3 things on this list by the end of the semester. And that will pretty much be it as far as carbocation fates are concerned. So it's not like we have to know 25 different carbocation fates. So I want you to think about what you know so far about organic chemistry and write down carbocation fate number 1. So you've seen a reaction that proceeds through a carbocation. Please think about what that reaction is and what happens to the carbocation. What is the fate of that carbocation in that reaction? Well, the reaction that you know is SN2. No, it's not SN2, it's SN1. And so in the SN1 reaction, what happens to the carbocation? A nucleophile adds to the carbocation. As in SN1. So be sure you know that. What I want to do now is I want to work through a problem where something else can happen to the carbocation intermediate. All right? So let's just come over here to this board, and let's start with the following compound. So let's do a little nomenclature here. What would you call this compound in terms of not really its systematic name, but more of its common name? So think about how many carbons there are and so on. What would you call this? This has 4 carbons, so it's a butane type of derivative, at least in a common naming scheme. So we'll call it butyl, but you may remember there are various isomers of butyl X. So focus on the carbon to which the chlorine is attached. What kind of carbon is that? Is that a methyl carbon, a primary carbon, a secondary carbon, a tertiary carbon, or a quaternary carbon? And maybe the answer will clue you in on what the common name of this would be. This carbon has 3 other carbons attached, so this is a tertiary carbon. And so we might call this tertiary, or just tert for short, tert butyl chloride. What was done with this starting material was to dissolve it in a mixture of water. That was 80% of the solvent. And then the other 20% was ethanol. And you may remember from some of the previous assigned problems, sometimes a co-solvent like ethanol, an alcohol co-solvent, is used when you want to use water as your main solvent. The problem is that a molecule like tertiary butyl chloride is not particularly soluble in water. So you need a co-solvent that is soluble, that is mixable with water itself, and that also helps to dissolve the compound. All right? So what I want you to predict, what would the substitution product be? And do you think the substitution product would be formed in an SN1 manner or in an SN2 manner? And let me just tell you that we're going to be concerned with the substitution product wherein water is acting as the nucleophile rather than ethanol. There's more water around, so let's
let's stick with the water. It's 80% of the solvent versus 20% ethanol. All right, so what I want you to write is I want you to write the substitution product, and I want you to tell me, you don't have to write the mechanism, although you could, but I want you to tell me what kind of mechanism you expect to be operative here as far as substitution chemistry is concerned.
In the substitution product, you're going to replace the leaving group, Cl, with the nucleophile, H2O. And then at the end of that, you're going to lose a proton. So the final product is going to be an alcohol. The product of substitution would be this one. There it is. And if you balance the equation, what are we missing? Well, we're missing the chloride, and then we're missing the extra proton from H2O. So if we were going to balance this, it would be a proton and a chloride. And if we wanted to be more realistic, the proton would be glommed on to water. So you could write that as H3O plus being one of the products and Cl minus being the other. So you definitely want to be sure you could write the mechanism out. And what would the mechanism be? Do you think it would be an SN2 mechanism? Tertiary alkyl chloride, no SN2. This must be via an SN1 type of mechanism that we get to the substitution product. Okay, so be sure you can, I won't write that out, but be sure you can do that. There's a key intermediate, of course, and we'll talk about that in just a minute. But first, let me tell you that yes, it's true, some of this was isolated from the reaction mixture, but there was also a second product, and the second product didn't have an OH group in it. It actually had a carbon-carbon double bond. So the other product is this. It's an alkene. So how does that product compare to the starting material? So if you were going to compare the molecular formula of the starting material to the molecular formula of this alkene, what has been gained, what has been lost? From here to here, we are somehow losing a proton again and chloride. So one way to think about this is we've eliminated the elements of HCl. So you see this carbon right here, if we think that this carbon becomes this one, starts out with 3 hydrogens, it ends up with 2 hydrogens, so we've lost an H from there. And then at this carbon, we've lost the chloride, and then these 2 methyl groups are still there, right? So sometimes this is called an elimination reaction. Why? Well, because you are eliminating 2 pieces and you're putting a double bond in. All right, so when you hear the word elimination, think to yourself, removal of something from one carbon, removal of something from the adjacent carbon, and the product of an elimination reaction will contain an alkene, a carbon-carbon double bond. Okay? So what I want you to do now we're going to have to get into the mechanism a little bit because we're supposed to be talking about carbocation fates. I want you to draw the carbocation that forms upon departure of the leaving group from tertiary butyl chloride. And while you do that, I'm just going to pause the video myself here so that I can erase the other board. All right, I'm back. The task was to take tertiary butyl chloride, let the leaving group go, and then draw the carbocation that results from that. So here's the departure of chloride. I'll go this way. So at this point, I'm going to end up with a carbocation. I'll draw it edge on like this. There's a plus charge here. The chloride has left. And now there's a 2p orbital, an empty 2p orbital associated with this carbocation. Can you draw it in? Well, that 2p orbital will be perpendicular to the trigonal plane. The trigonal plane of this sp2 hybridized carbocation is perpendicular to the board. So here is the empty 2p orbital associated with that carbocation. And then, for practice's sake, I recommend that you show how you get from this carbocation plus water to that final alcohol, tertiary butyl alcohol product. Remember, water adds as the nucleophile first, and then there's a deprotonation step at the end to get to the final SN1 product. So be sure you can do that. So certainly, remember we talked about carbocation fates. It wasn't that long ago, maybe a few minutes ago, but remember what fate number 1 is? Fate number 1 is you can add a nucleophile, and that would give the substitution product. We won't do that here, but you should definitely be able to do that. And then we have a second carbocation fate. We'll fill in a description of it in just a second. But I just want to introduce you to a little bit of terminology here. This carbon, the carbon to which the leaving group was attached, let's call that the alpha carbon. Alpha is the first letter of the Greek alphabet, of course, and we'll give that priority to this carbon. And then attached to alpha is, guess what? Beta. So here's the beta carbon. And we said elimination involves loss of a leaving group from the alpha carbon and loss of a proton from the beta carbon to put a double bond in between alpha and beta. Okay? So we've gone part way. We've gotten to this carbocation. The second carbocation fate then might be described in the following way. Lose H plus from next door. So if you're alpha, the next door position is beta. So can you do this? Can you show the loss of H plus from the beta carbon? And we're going to make a double bond. All right, so we're going to lose H plus from next door to form an alkene between alpha and beta. So can you do that? And my first hint is it's hard to show that when you just have this written out as CH3. The first thing you might want to do is to just draw out the CH bonds at the beta carbon. So try doing that. And then remember, a proton is not just going to fall off. You need a proton remover. What do you call a proton remover? What's a slightly more chemically sophisticated way of referring to a proton remover? You need a base. So think about what is the strongest base I have in this vat. Okay? Don't just invoke some crazy base that's not even there. Figure out what is the strongest, most available base that I have. Okay, so let's start over here. I'm just going to hang on. Here we go. Let's beautify this a little bit. So let me put in my 3 hydrogens. Here's one of them, and here's another, and here's another. What did you conclude was the best base you had around? Chloride? That wouldn't be the best choice, because if you use chloride as a base, you're going to generate HCl. HCl in aqueous solution doesn't make sense, right? Because you know HCl is fully dissociated. So if you chose chloride, think again. The best base I have around here is just H2O. There's more H2O than ethanol, so that's why I pick it versus ethanol. But so here is my best base. Let's put the lone pairs on here. So can you push the arrows? We need to use our best base to remove a proton from beta, and we need to make a double bond. And here's a slightly more sophisticated stereoelectronic question. Remember, stereoelectronics has to do with the positioning of electrons in three-dimensional space, orbital alignment, that sort of stuff. I've drawn the hydrogens at the beta position to suggest that there's one of the three hydrogens as drawn that is best situated for this process of forming a double bond between alpha and beta. So if you're going to deprotonate one of those three hydrogens, see if you can pick the stereoelectronically preferred one. Well, it's this one, because this sigma bond is aligned with the 2p orbital. So let's see how this goes. Here comes one arrow, and then I'm going to use these two electrons to make a double bond. Think of this movie, right? So I've just shown you the beginning of the movie. As this movie proceeds, what happens to the hybridization of the beta carbon? It starts out as what, and it ends up as what? The beta carbon starts out as sp3, and by the end of this movie, it's sp2. There's a carbon-carbon double bond between alpha and beta. So here is alpha, here is beta. Notice alpha started out sp2 and it ends up sp2. And then these hydrogens, during the course of this deprotonation, they move somewhat so that we end up with this nice flat alkene. The plane of the alkene here is drawn perpendicular to the board. And this is the second carbocation fate, and it is called elimination. Okay, so look what happens. The leaving group leaves, we make a carbocation. Now this carbocation has two possible pathways that it can react by. It can go through substitution, addition of a nucleophile, that's carbocation fate number 1. That ultimately leads to the SN1 product. But there's also a second pathway, which may be quite competitive with the first, in which you lose a proton, this, from next door, from the beta position. Notice this is lost as a proton because it leaves its pair of electrons behind. You lose a proton from next door, you make a double bond, and that carbocation fate is known as elimination. So you now know 2 of what will eventually be 3 carbocation fates. Fate number 1, add a nucleophile to the carbocation. That's the one you're already familiar with. And here's this new one. The carbocation can undergo elimination. That means loss of a proton from the carbon next door to form a double bond.